I will begin with a word of prayer. Everyone was here, so everyone will be here again. I'll start. Heavenly Father, we thank you for this day, and I thank you for the students. Just ask you to help us to use this time wisely to review for the test, Lord. In my prayer, Lord Jesus. Amen. So, yeah, I guess it's just as well today's, like, this is a test week, but since I'm only partly able to talk. So, Mary, for you, it's just, you know.
Here, it's Violet's.
Okay, Violet, can I have it? Shane, Jordan.
Great job, guys.
So, this is one of you're reaping the benefits of me being sick, which is I don't have enough energy to grade your mission.
Why do you always do it to the missions that I actually work on? So the missions that I don't have time to finish.
That just makes it more awesome.
No, it doesn't.
It's kind of funny.
But you're learning about it. Your brain cells are, you're forming new brain cells.
Well, I look through it and I say, okay, well, Violet has finished all of the problems, so I don't need to grade this one. That's like my algorithm. Let's see. Did you? How about this? If I look at this quiz one, what am I going to see? What am I going to see? Oh, what's this? Oh, no solution to a certain couple problems. This one I'll have to grade. All right. Yes.
No, Violet. What have you done?
All right, so let's look through the solution to quiz one right quickly. So I did recycle some of these problems, so this is partly from last year. Multiply by the conjugate, I get 8. I get that. This one here, triangle, 1 up, root 3 over. That makes a 2 here. So that means that the cosine of this angle is like root 3 over 2, and the sine of this angle is 1/2, like, you know, trigonometry. So anyway, so when I calculate the 7th power of root 3 plus I can do it like this. Of course, that's pi over 6, right? And then, so 2 to the 7th, and this to the 7th power by de Moivre's theorem, and you get, you know, 7 pi I over 6, which I could rewrite like this. E to the pi I is -1, and so minus 2 to the 7th times that, which gives me this. There's the Cartesian form, and here's the Cartesian form. So, yeah. Now, there are many right ways to write the answer there, but I did say find the Cartesian form, so I would like the Cartesian form, you know. So there's that. Log of -2i is natural log of the modulus of 2i plus I arg of -2i. Now -2i is down here, which has a standard standard angle of minus pi over 2. And so that's what it is. Notice it's the capital log, so it is a particular value. It is not a set of values. Now we got z equals 3 plus 4i. Find the polar and Cartesian form z to the 42. So the magnitude of that is 5. And so we get 5 to the 42 times e to the 42i theta, which is this. So there's the polar form of the answer. And then here is the Cartesian form of the answer by Euler's formula. So there's that. Z to the 5th equal to 32i. We solve by looking at the principal 5th root and then multiplying by the principal 5th root of unity to the power 1, 2, 3, 4. And that gives me, so the principal 5th root of 32i gives me 2 e to the pi I over 10, which is easy to check. If you take the 5th power of that, you get 32 times e to the pi I, but e to the pi I is -1. Excuse me, e to the pi I is, wait a minute. Hold on a second. To the 5th power, we get e to the 5 pi over 10, which is e to the pi I over 2. E to the pi I over 2 is I, so you get, you know, 32i, which is what we want, the 5th power. Whatever this is, the 5th power of this as a check should be back equal to 32i, right? If we did it right. So, fun thought, this could be when you're taking your test, right? So this, if you didn't change things, right now, you guys would be taking the test. How would that be?
Real bad. It would be really bad.
That would be bad.
This is not a good day.
No, this would have been really, really bad, so. I guess, thank you, Dr. Sperano. So it's all his fault. So here's the fifth root of unity, principal fifth root of unity, e to the 2 pi over 5. He made a test last week, which bumped things around a bit. Oh, so yeah, thank you for me getting sick. Yes. So, yeah, it is all Benjamin's fault, his love of La Coretta and sharing soda. I almost didn't get soda. Last Sunday, but then he made a particular face. You've seen this face. This. It's a very particular
Who made the face?
Benjamin.
I knew it was Benjamin.
Oh man, that face. You got to get soda. So, anyway, so I multiply, and the reason I changed this e to the 4 pi I over 10 is because it's easier to add 4/10 to 1/10 than it is to add 2/5 to 1/10. Because when you're multiplying by powers of omega 5, you're adding 4/10 each time. Plus 4/10, plus 4/10, plus 4/10, right? So plus 4/10 gets me to this, plus 4/10 give me to that, plus 4/10 give me to that, plus 4/10 give me to that. And these could be simplified, right? But I did say leave your answers in polar form, so don't simplify, right? Like for example, this one.
It was?
Yeah,
I
this
don't.
is-
I
This
can't.
is a quiz.
I don't remember.
Mm,
I can't remember.
Problem 3.
Did I do that one?
mm,
Can I look at my paper?
mm.
No, I need to see if I did it, but I don't remember.
Oh no.
Looks like I didn't do as well as
Oh no, don't.
Oh, you want to look? Well,
That's Rachel's right, not mine.
Oh no, let's not talk about it out loud. Look at it. I don't know what I did.
I mean, I could either look at it as being 20% wrong, or I could look at it as being infinitely wrong.
Yeah,
That means to be 20% right or infinitely wrong, depending which way you want to look at it. But
yeah. Yeah, I can see it.
because you added a set of values, which is not accurate. So
I must have did this last week, so I don't remember.
it's okay. So the key here is I'm using like. So early in this course, we derived the solution to, a fifth, like the nth power of z equals to w, and we worked out the nth root of w, and then the nth root of w times principal nth root of unity, and then that ranges powers of the principal nth root of the unity from 1 to n minus 1. Anyway, so that's what's at play here. The simplest instance of this, of course, is like the 1/2 power gives us just plus or minus the principal square root, right? If you don't know what I'm talking about, you need to figure out a way to note about it. I don't know. This one here, you've got a closed disk up here, radius 3. You have an open disk, radius 2. And if they were both open, it would be disconnected because there would be no connecting point. But because that point is thrown in, I can take any point up here and pass it through the line that goes through the curve that goes through that point and get down to any point down there. So it's connected. Yep.
For, I'm gonna like for in this when you come to the definition of connected, I wrote down that there does not exist, so like with your two discs,
Yeah.
where the intersection of the two discs is empty.
Mm-hmm.
And when I was looking at this, so like if it's not connected, then
Hmm.
the intersection is empty, right?
Hmm.
But the intersection is empty, technically, right? When you're looking at this, but it's connected based off of the definition of like the polygonal path,
Hmm.
right? You know what I mean? I couldn't figure out what I was missing, but I mean, obviously my polygonal path is connected, but in terms of intersection, it's not. Unless I wrote something down wrong,
Hmm.
or I'm interpreting something wrong.
Could you maybe say that you would have to take the intersection of each set in its closure?
Oh gosh.
It may be that I have to have a pair of open sets whose union is the space. I mean, the top set's not... You've worried me, Mary. Let me think about this some more, okay? Yeah, I have to get back to you on that. Because I see the merit of what you're saying. And my immediate thought is, well, they're not a pair of open sets.
Right.
And that's the issue.
Okay.
But if I think about the union of these two sets with respect to the relative topology, they are both open. I think because they're... Well, no. The relative, so the relative topology is... Oh, okay, we're off track. Let me stop. So, let me stop.
Should we just rely on the polygonal path?
Yeah. If it's any consolation, when I put that on last year's test, it stumped a lot of people. But mostly because they didn't draw the discs right. Most people who drew the discs right got it. This one's just ugly. I don't really want to talk about it. But here's what I did. I completed the square, basically, in the quadratic, in z squared. And then once you have that, you have this. And then I called this beta squared. I called that gamma squared. And as such, it goes like this, where beta and gamma is defined below. It's unpleasant.
Yeah, I agree.
It's unpleasant.
I did that wrong.
But nevertheless, the methods that I used, you should be able to use if I was to maybe, I don't know, conjure up a less ugly problem. You should be able to use the method that I used here for a less ugly problem. For example, like, it's not hard to make this less ugly. I don't know, suppose you're factoring z to the fourth plus 16i instead. All of a sudden, then it becomes less annoying. Still annoying, but... Because if I put 16i there, then you can use the roots of the fourth roots of like minus 4i. You know what I'm talking about? So if I'm going to factor, for instance, z to the fourth plus 16i, right? I want to factor that. So if this is my polynomial, then I can write p of z as z minus z1, z minus z2, z minus z3, z minus z4, right? I mean, that's, we're working in the complex numbers, everything factors, fundamental theorem of algebra, right? Where what? P of zi equals to, let me get a j, equal to 0. So really, you're just trying, if you could find the solutions to that, then you factored it, right? So we're trying to solve z to the fourth plus 16i equals to 0. If I can find 4 solutions to that, I just put those 4 solutions up here, chunk, 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 and I factored it, right? That's it. Or in the words of your silly textbook, I've deflated it. But no one says that. Anyway, so z to the fourth equals to minus 16i. Which is to say that z is an element of the fourth roots of minus 16i. How do you actually calculate that? So this is literally the fourth root, the principal fourth root of minus 16i, and then I times that. I'm going to call this thing Pac-Man. I times Pac-Man, I squared times Pac-Man, I cubed times Pac-Man. Now why I? Because I is e to the 2 pi I over 4 in this case. How do I know this? I don't know, I just know. I guess it's because I did this before at some point. I'd like the same for to be true for you in many instances. You know? This is why I give you homework. Try to make you familiar. So, of course, I squared is minus 1, and I cubed is minus I. This was uglier in the earlier problem we looked at because it was fifth roots. So like the e to the 2 pi I over 5 is nothing particularly pretty, you know? E to the 2 pi I over 4 is I. So it's a particularly nice thing to ask about. Anyway, the question remains, what's the fourth root of minus 16? Can you tell me that? 2. Yeah, 2. So the magnitude of this is just, well, okay, so that works out to 2, is your point. And then we've got e to the, I divided by 4 arg of minus 16i, which is what? What's the argument of minus 16i? This should not take you more than 5 seconds at this point.
Minus pi over 2.
Minus pi over 2, yeah. So this is minus pi I over 8, because I got 2 times 4 is 8. And so there you go, that's the Pac-Man. So basically, to factor that, I would have z minus, 2 e to the pi minus pi I over 8, z to the plus 2 e to the minus pi I over 8, z minus 2i e to the minus pi I over 8, and z plus 2i e to the minus pi I over 8. Sorry, my handwriting is degenerating, but you get the idea, I hope. How's it going to go on? Excuse me. Here we're supposed to check what? That component functions satisfy the Cauchy-Riemann equations, right? So there's a little bit of calculation involved here, isn't there? Let's see. So what did I do? I calculated z squared, right? We know that. And then I used the adding angles formula for sine xo. Hey, did I ever make you guys prove those?
What?
The adding angle formula for sine?
I think for sinh.
Cinch I did? Okay.
Wait.
Anyway, you could prove those. You have several ways you could prove it. You could use the adding angles. You could use the law of the, well, I guess the question is, how can we give a non-circular proof? I forget what we did first. I did in the notes? Oh.
We just defined sine of x plus iy as...
Oh, we defined sine of z as 1 over 2i e to the iz plus e to the minus e to the minus iz. Yeah. So you could use that and the laws of exponents to derive this, I suppose. But anyway, let me focus here. So we, unless I say otherwise, you're allowed to use laws of exponents and the adding angles formulas for sine and cosine, not a problem, okay? So doing that gives me this and that. But you notice that I did cosine. I had like cosine of 2ixy, which actually gives me a cosh. And I had, over here, I had sine of 2ixy, which ends up giving me this I sinh and a minus, which that, well, excuse me, that, and that plus. There's no minus, my bad. Anyway, so there's your u and your v, and you can differentiate it, and you can check it out. Ux equal to vy, and vy is equal to minus ux, I think. So it satisfies the Cauchy-Riemann equations, and as such, the derivative is that, which is just what you think it should be, right? So in terms of the Cauchy-Riemann equations, we had f prime of z is ux plus ivx, which when I put that into practice, I've got this and this, which I can factor out that, which then is undoing the law of cosine, the adding angles formulas for cosine. This is that. Well, really just using the component functions for cosine. So I guess what I'm picking up on here is it would be smart to know, to have a clear path how to derive the component functions for sine and cosine of a complex variable, the complex exponential, right? How to get from cosh to sinh, and how to get, how to get from cosine to cosh, how to get from sine to sinh. You know, the more of this that you have settled, the more you shouldn't get stuck on certain questions, I would say. But anyway, there it is. Now, suppose the problem had not been stated as such. What if I just said, show that f of z equals sine of z squared is complex differentiable and find its derivative? Would this be the way to do it? No, this is an insane way to do that. You should use the Wirtinger calculus. You should say, well, the partial derivative of f of z with respect to z bar is clearly 0, therefore it's complex differentiable, And the partial derivative with respect to z is simply 2z cosine of z squared, which is f prime of z in this instance, done. That would be the smart way to do this, if you were given the freedom to do it that way. With the problem as stated, we had to do what we did, right? So,
Is there a clear way to see without decomposing the function into a bunch of other stuff, whether it depends on z bar?
I mean, you calculate partial z bar of it. That's what to do. So if the function is manifestly a function of z and known functions, then you can calculate the derivative with quotient rule, chain rule, product rule, all that stuff. On the other hand, if your function's expressed in terms of x and y, then partial z bar is a specific partial differentiation operator defined in terms of partial derivative with respect to x and y. So as such, you can calculate the partial z bar derivative in that regard. So you got two different worlds you can live in. You can live in the world of z and z bar, or you can live in the world of x plus iy. And either way, we've got a way to formulate z bar.
And if you have z and there is no z bar expressly there, there's no weird functions like modulus, then we can just say it's 0.
The partial derivative is 0. Yeah, I think that's pretty much true. In as much as, like you said, it's not like modulus of z squared. So you gotta be careful. There could be, I don't know, if there's a way to hide a modulus or something. Is there a way? I don't know. Like 1 over, I guess it could be something like 1 over, I mean, if you had something like 1 over x squared plus y squared, you know, plus 7, is it complex differentiable? You know, something like that. Well, that's a hidden modulus of z squared, right? So you're to rewrite that in terms of z bar explicitly. It'd be like 1 over z bar plus 7. So, yeah. Which I think is what you're telling me not to do. So, yeah. But, oftentimes, well, anyway, let's just go on here. I'm not going to. This one, I tried to solve this. I tried integrating ux equal to vy, and it was unpleasant, like really unpleasant. So I thought, that's not the way to do this. I should just try to see what this is the component function of. And so I thought, all right, well, if I look at a plus ib times x plus iy, I get that, which I can see bits and pieces of that appearing. So if I do e to the, like, a plus ib times x plus iy, I get this. And then I'm like, oh, wait a minute, that's the thing I'm given. So I need to make this, I need to make this the real component of some function. To achieve that goal, I multiply this equation by minus I. You see, minus I times e to the cz, where c is equal to a plus ib, picks up the u that I'm given as the real part, which makes that the harmonic conjugate. So, yeah. This would be a tough question on a test. It was a reasonable question because this was a quiz that was take home. But outside of that context, this is kind of nasty. This one is a pretty standard test question. Find the real valued functions u and v such f equal to u plus iv given. This is just a plain old find your component functions question. Probably it would be better if I put this question before the earlier question, maybe. I don't know. I mean, I'm not sure the order of these questions is optimal. But anyway. So yeah, I used the adding angles formula for cosine, and then I switched cosine of an imaginary to cosh of a real, and likewise sine of an imaginary to I times sinh of a real. So you need to know those relations between sinh and sine and cosh and cosine. Know them carefully. Be able to use them. They're helpful. This one here, you got log of iz plus 2. So we just, you know, you're looking at log of 2y, 2 minus y plus ix. So we take the natural log of the modulus, which is 1/2 the log of the sums of the squares of the, you know, imaginary and real components. And then I'm looking at arg of this animal over here, or whatever that is. So there you go, u and v. So if the question doesn't touch on the details of the angle, you don't have to figure out how to express it in terms of an inverse tangent or an inverse cotangent. So you just have to use your judgment whether or not you need to dive into the details of like how to actually calculate the argument. It is acceptable, of course, to use argument. That is a function that we have defined, and as such we can use it. You know, we don't have to go back to real trigonometry every time. On the flip side, it would have been bad form to not do it here. Like, I would not have been pleased if I had just gotten arg of 3 plus 4i here instead of 42 inverse tangent of 4 over 3. Like that kind of problem, I actually want you to do the trigonometry. But in the midst of something like we were just looking at, it's not important to me that you make clear the like 4 different cases that are necessary to define this arg over here, you know? Yeah?
So if we accidentally did trigonometry for that one on the test, would you still?
This one? Well, I mean, I will be sad for you because that would mean that you didn't do something else you were supposed to do if you took the time to do that. You know, I mean, so, yeah. I mean, it depends on what, I don't know. Try to convince me you know things. That's your general goal in the test, right? So here we've got, what we got here? Function is holomorphic on some domain, explain why, and calculate complex derivative. Otherwise, explain why the function is not holomorphic on the domain, blah, 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 blah. So I first of all have this handy dandy x cubed minus y plus i x squared y. There you just calculate ux and uy, and ux is this, uy is that, vx is that, vy is that. And the Cauchy-Riemann equations look like this and that. This can be solved by x equal to 0. And y equal to plus or minus 1, I guess. Or we could have, we have to have y equals plus or minus 1 to solve this. So given that, we're forced to have x equal to 0 up there, I believe. Is that what I found? Oh, we could also do x is plus or minus 2/3. Yeah, there's that. I was missing that. So this is forced upon us by the second equation, inescapable, which means that we're up against this, which has either the solution 0 or plus or minus 2/3. So there are 4 points where the Cauchy-Riemann equations hold. So it's complex differentiable at those places and nowhere else, which means it's nowhere holomorphic because there's no open set anywhere where it's complex differentiable. So it's nowhere holomorphic. This one here, you've got cosine of a z bar, which has a z bar derivative, which is non-zero, unless what? Unless you've got z is equal to 0 here. So the only place where it's satisfying Cauchy-Riemann equations is the origin. So it's not holomorphic on any domain. This one next here, I can just differentiate. It only depends on z, so the partial derivative with respect to z bar is 0. Yeah.
What about for B?
Sorry, what?
What about for B also? ZZ bar equals K pi.
ZZ bar equal what?
ZZ bar equals K pi.
K pi?
Yes.
What are you talking about?
Then the stuff inside the sign is K pi, or K is an integer.
Is this a joke?
And B.
K pi. Oh. Oh yeah, very good. I missed it. But still, my conclusion's still right, but you're right. I am missing, this is bad. You have to take like all of my credit away because I've only got like one of infinitely many cases where it's holomorphic, but it's holomorphic on, so I've just got k equal to 0, but you're right, k could be 1, 2, 3, 4, blah, 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 blah. So circles of radius, so like, what he's saying is if this is equal to k times pi, then you've got the Cauchy-Riemann equations hold, that's true. So that's x squared plus y squared equal to k pi. So we're talking about circles of radius k pi out to infinity. But the thing is, no matter where you go on one of those circles, you always, if you take any open set, you're always on points outside the circle, which means you've got nowhere holomorphic. You've got no place where you have an open set on which the function's complex differentiable. But thank you. Yeah, this is very good. Very good, Shane. My solution is missing quite a bit. Now this one here, again, this is a rational function in Z. They're holomorphic on their domain in C, basically. So the place where it's not holomorphic would be at like plus or minus 1, I think. That's it. Excuse me. My answer is missing a bit there, right? I'm sorry about that. I'm telling you in words, though, yeah. So here, we've got principal log times z squared, which, if we can differentiate it, differentiates like so. And the deal is we need 2z plus 1 to not be in the bad spot for the slit complex plane, right? So essentially, we need 2z plus 1 to not be an element of minus infinity to 0. And so you can work out what that means. That means that if you were to set that equal to minus t, you get, 2z plus 1 equals to minus t, which is 2z equals to minus t plus 1, or 1 minus t. So you can't have z. Oh, goodness, I can't do it in my head. The picture's fine, I think, but logically speaking, we got 2z plus 1 equal to minus t, which means we get z equal to, minus 1. Yeah, minus 1 minus t over 2. These are the bad spots. And so at t equal to 0, that starts at minus. At t equal to 0, you're here. And then as t goes on, you go and so forth and so on. All those points are places where the log is discontinuous. And that, of course, is signature of the fact that it's not complex differentiable at such points. But it's holomorphic everywhere else. So there's a branch cut, so to speak, here. Sorry. And again, my solution's missing a bit. I should say, okay, so this has is it manifestly a function of z alone? So I can apply the rules of calculus on the intersection of the domains of the functions in play. In this case, the weakest link is the log, right? Everything else here is z squared or 2z plus 1. Those are entire functions. There's no limitation whatsoever on those. It's simply the log that's limiting the discourse. Here, the question is, I think this would be principal square root, right? So principal square root's the weakest link here. And, okay, actually it's a little bit more nefarious than that, isn't it? But certainly this means I can only differentiate on the slit complex plane because the domain of the principal square root is c minus. It's missing the positive real axis because we built the principal square root with the principal logarithm, right? It's like the formula for principal square root is the square root, the regular old square root of modulus of z, e to the I arg of z over 2. Like that's the formula for principal square root, and that's discontinuous on the negative real axis. So this is holomorphic everywhere except for that slit. But we got to think about tanh. Like tanh has problems. Tanh is what? It's sinh over cosh. Is cosh ever 0?
No.
Oh, but it is. Because cosh is cosine of iz. Is cosine ever 0? Surely is. So in fact, there's infinitely many places where cosh is 0. As such, there's infinitely many places where tanh is not defined. So, yeah. And this is a sort of a yoga to remember of sorts, which is that cosine is cosh and sine is sinh in complex. That's not exactly true, but it is a useful mnemonic to keep you out of some troubles. So yeah. Here's the proof that the derivative of the square root is 1 over twice the square root of the principal square root. Why is that true? Because this is the definition of principal square root in terms of the the power. So like we proved that our definition for principal square root and the other definition in terms of 1/2 power were equal the other day. We proved that these two formulations were equal. You may or may not remember that, but we did. And so this is equal to that. and that I can differentiate using chain rule and so forth. So, actually, we proved that the derivative of the nth root function was 1 over n times the nth root function to the, oh golly, we proved the power rule holds for the nth root function is what we did. All right, but I don't seem to have, oh yeah, see, so I dodged the bullet here, but you know, truth be told, if you wanted to discuss, did I say I had to discuss the holomorphicity at the start of this problem? Oh, why am I'm being burdened by what has not been. This is not good. Let's see here. Let me stop. So I'm sorry. I'm distracting us with a more difficult question, which is where is that function defined? This is tricky. So here, problem 10. This is a fun test question. Like, how do you calculate this limit? Because of course, if you take a real perspective, it's rather difficult. But if you recognize what it is, which is just the difference quotient of sine, well, the derivative of sine is cosine. So cosine of 0 is 1, and that's it. Yep.
So we could check that with L'Hopital's rule.
We don't know L'Hopital's rule. There is no L'Hopital's rule. If you want to prove L'Hopital's rule, we could do that. I could put a test question, prove L'Hopital's rule. That sounds like a good question.
Because we haven't talked about L'Hopital's?
Yeah.
Oh, okay.
So what I did is I showed through, so I split it up into component functions, and then I checked the Cauchy-Riemann equations. Does that also work?
Cauchy-Riemann.
Because that means
But
it has to be complex differentiable and therefore continuous. So then the limit exists, and we can just use the real one.
I'll have to look at it. That might work. I mean, but so you looked at this or no?
Yeah, that looks like it, yeah.
So how did the Cauchy-Riemann equations help you? I'll have to think about it. I don't know. That doesn't. So you looked at the Cauchy-Riemann equations for what? For what? For this function?
Yeah, so I split it up into U and IV down there.
Oh. So your point was. Wait a minute. Like the function sine z over z?
Yeah, like you showed that's complex differentiable.
At 0?
At 0.
But this function's not defined at 0. Like at 0 over 0. I mean, you could define a function g of z such that g of 0 is whatever it should be, and g of z is sine z over z, and then you could prove that that function is continuous, probably in the way that you did. And then you can define the value of it at 0 to be the limit of the component functions elsewhere. That would be reasonable. So if that's your solution, then like, okay, but
I don't remember.
yeah, I'll have to look, but that's interesting. That's interesting. But it's easier than that, right? Like it's the difference quotient, so work backwards. Yeah. Let's see here. So here we have z to the fourth, and I give you s sub alpha is basically what? It's like a quarter plane, right? It's the quarter plane that goes from angle alpha to angle alpha plus 90 degrees, so to speak. I'm sorry, pi over 2, what was I talking about? And so show that f of s alpha is equal to f of z such that, well, what's there to show there? I am confused. Oh, is the complex plane. So you get everything. All right, yeah. So you get, any questions about this? I don't really want to spend a lot of time on this problem today. Because, no?
Are you going to post all of these solutions?
Yeah.
Or, okay.
Yeah,
Then no questions.
no questions. So like, I mean, let me just talk about it a little bit, but so f of s alpha is, you're feeding points in S alpha into the formula for f. F is the the quadrupling function, right? So you take the fourth power of the input, and when I do that, I get r to the fourth e to the 4I theta. But the thing is, if theta is ranging between alpha and alpha plus 2 pi, multiplying that by 4 shows me that 4 alpha is less than or equal to 4 theta is less than or equal to 4 alpha plus 2 pi, which shows you that 4 alpha ranges over a full 2 pi cycle of angles, which means that this is covering every single ray, right? It's covering every single ray, and S, on the other hand, is covering every single magnitude. Well, that's the whole complex plane. That's it. And of course, if you wanted to, you could just like, you probably could divide up into, if you wanted to be like, well, anyway, that's a good proof. So let me just leave it at that. You could do things with the fourth root, I suppose. Part B was what? I forgot what part B was. I guess I'm supposed to show that f is 1 to 1 if you restrict it to S alpha, so that's the proof of that. And then C, I'm about to remind myself what C was. So I said solve w equals z to the fourth for x and y. Is that what I said? So we're trying to find the inverse function. So w is u plus iv. W is equal to z to the fourth. So that means z is an element of w to the 1/4. And so if you look at it, the range of the principal fourth root's over here, and then I times the principal fourth root's up here, minus the principal fourth root takes its values over here, and minus I, the principal fourth root, takes its values over here. So the range of the principal fourth root and its brethren each occupy some sector in the complex plane, for what it's worth. What was I trying to do? I forgot what I was trying to do. I was trying to solve for x and y, right? I'll get to it eventually, I guess. So I argue that I can simply use the alpha fourth root of that z. Do I ever get actually to the x and y? Oh, here it is. So the solution solving for z is the principal fourth root of w, the alpha in the alpha sense, which by that I mean this, which is the eighth root of that guy, cosine, sine, and then so that's my x and that's my y. Yeah. I'd say this is a hard problem. Let's see here. Let me go on, like I said. This one, on the other hand, is a much more testable problem, I would say. Like, this is a reasonable question for a in-class time pressure test. So you're supposed to find a branch of the multiply valued function, which is holomorphic on H. So again, the issue is that we can't let the input to the logarithm be in the place where the logs of alpha has a discontinuity, right? So what I do is I put the input 3z minus 1 equal to te to the alpha. That's the bad spot for logs of alpha, right? That's the place where it's discontinuous. That's the place where it's not holomorphic. So I'm looking for the trouble. So solve for z, I get 1/3 plus that. So what that does is it puts me at 1/3, and then I'm doing plus t over 3 times the ray, which goes in the direction of e to the I alpha, like that. So as long as I make my alpha between, say, 0 and pi, I'll be fine for this example. There are infinitely many choices that you could reasonably make here. So like some of you told me, I'm going to use the principal logarithm. That's a great choice. That's a fine choice. It's right on the edge of what works, right? Because the principal log would put this guy like that, right on the edge of where you're trying to get holomorphic. You want holomorphic up here, according to the problem statement, right? So if you put it here, you're just on the edge of what works, and that's okay. Now, for part B and C, I was making it more difficult than I needed to with one of you talking about it, I was thinking, well, I need to figure out where what the solution of this looks like, you know? And that's quite challenging to figure out exactly what that looks like. But what isn't challenging, what's actually pretty simple, is figuring out where it starts. See, where the place where it's not holomorphic starts, the initial points for the branch cuts are given by t equal to 0, which is plus or minus the square root of I. Well, that's e to the pi I over 4 and the negation of that, which are these 2 points, right? So if I'm trying to make this function holomorphic up here, I cannot do it because I've got this pesky branch point right here, and it's unavoidable. So it's impossible to choose a branch of this which is holomorphic on the upper half plane. You just can't do it. So thankfully I said if possible. And very similar comments apply to part C, because here you're feeding it z to the 4th plus 1. If that's equal to excuse me. So I think I just found the branch points for the principal log. If I use principal log, for instance. Oh, no, I'm sorry. I'm just looking. Where it equals to 0 tells me where the branch points are. And like what happens after that, like the other points that are lost, it will depend on the choice of angle. It might make the branches go off like this, or like that, or like that, or who knows. I worked out with Mary that if we choose, I think, pi over 2, we end up with branches that go like this for this one. So you end up losing an x. But that is not obvious without about a page of work. So anyway, if that problem appears on the test, it will be called Mary's problem. So.
Would you put all 3 parts? Like if you,
There's a little one for C up there, corner.
no, would you on the test put all 3 parts, like all 3 different, or conceptually you just want us to hit like do you?
Well, I like the one where it actually works out so you can actually choose a branch,
Right.
and it's not too complicated.
Okay.
For that to be reasonable, it almost has to be a linear input
Okay.
into the logarithm, unless I think it's something more nefarious before Thursday. Maybe I'll get my strength back and you'll get a proper test.
Okay.
I mean, maybe. I'm going to Texas Roadhouse tonight. Maybe that'll make me better.
I don't know. Lots of grimy menus.
You sound hopeful, you monster. Let's see here. So let us go back to the homework. What do we do in homework 1? What did we do? We solved equations, we proved a binomial formula, we calculated magnitudes, we put things in polar form. All these things are still with us. What else we do? We did more stuff with polar forms. We found sums and identities for sines and cosines. We worked out the quadratic equation from first principles, I hope. We solved the cubic equation. We considered the geometry of an equation in complex variables as it relates. Remember, this was what? This distance plus that distance from the point 1 plus I, and the distance point minus 1 minus I is held fixed at 4. This was the set of all such points was remember? An ellipse. If it was the ellipse, if it was difference, it would be if it was difference, it would be hyperbola. If you take 2 fixed points and you look at the locus of points which are the same distance from both points, that gives you a what? Maybe work it out on the test. Let's see here. So it should give you a line. It gives you a line. Right? Like you're in geometry, aren't you guys? Remember that thing you do with the compass? Like and then because you're taking 2 points, and you're running the compass to find the distance that's the same from both points.
You know, we're not using distance.
You use compass. You don't use straight edge compass construction?
I don't know what that is.
I don't know what that is.
What in the world? I thought you guys did Euclidean geometry to start with. Has he changed it up? Are you doing a fine featureless geometry to start with?
It starts out general. It starts out with incidence geometry.
Oh, okay, well, good. He was previously teaching it, so it started with Euclidean to make it a more gentle on-ramp.
It's not gentle.
Oh! The math education people are no longer with you, so it's a real course. Let's see here, so, yeah, that must be it.
It's like one or two.
No offense. Wait, no, you're an engineer, so, yeah, never mind. That's right, yeah. Very good. So, here's a good problem. Prove that the conjugate of the product is the product of the conjugates. That's a good problem. And here's some fun, basic, formal stuff. Yep.
Do you know roughly how many questions would be on the test?
Oh, yeah, definitely enough. So, why do people always ask this question? It doesn't have any meaning. So in here we had calculate, little log, big log, cosine, third power, 1 plus I power here, solve these, find solution sets, right? Geometry, like is this closed, open, neither, connected, star-centered, compact. So this is just a brief review. This is important. Problem 29. We have one function. We had 4 different ways to look at complex differentiability. Limit of the difference quotient, the method of Carathéodory, the Cauchy-Riemann equations, and of course, last but not least, the Wirtinger calculus, right? We've got these 4 different methods of understanding complex differentiability. And this problem is actually very easy if you take the right approach. Here, let's look at that for a second. Number 30. So if f is complex differentiable at z naught, goodness gracious, then by the theorem of Carathéodory, f of z equal to f of z naught plus the limit quotient function phi of z times z minus z naught, where phi is continuous at z naught with limit of the derivative. This is given to us by the Carathéodory criteria for differentiation. So I have all of that by Carathéodory. And so if I calculate the limit as z goes to z naught, I calculate the limit as z goes to z naught of that. But this is 0. This is f prime of z naught. And that's f of z naught. Bam, f of z naught, done. Continuous. Right? This is not bad, right? I mean, so proof of complex differentiable implies continuous becomes very, very simple if we use the Carathéodory business. All right. Of course, we also talked about the shape of a matrix. When is the matrix, a matrix which corresponds to a left multiplication by a complex number? We had some problems. We looked at that. We looked at how to calculate the Jacobian, how to understand whether or not the Jacobian is the right shape to be the Jacobian of a complex differentiable map or not. Oh man. So mission 3 solution, what do we do in mission 3? We did, well, fun basic stuff at the start, right? Like problem 31 is so easy. 31 is so easy. This makes a great test question, something like it anyway. If you've got a holomorphic function which is purely imaginary, prove it's constant on a domain. So u equals iv, well, to say it's pure imaginary means u is 0. But then the Cauchy-Riemann equations hold, so you've got ux is 0, uy is 0, but that means vx is 0 and vy is 0. But if vx and vy are both 0, that means that v is constant because its gradient is 0 on the domain. So there it is, yeah. And I think I stole this one from, I stole this solution from you, Mary, maybe? I think. But then I thought about it and I realized, it's okay, but there's something a little bit funny in terms of, it's not wrong, it's just, I have to,
The limit part where you change.
it's where I trade my g of z naught plus h for my g of z naught plus k, and I switch from the limit of h to a limit of k. Like that step right there is like, That's where I'm a little bit, yeah. So here's the proof using Car-Theodori. So I have, I can write f in terms of the Car-Theodori function. I can write g in terms of the Car-Theodori function. And I can compose them. And when I do that, I get this formula, which then I can take the limit of. And it's a little bit more rigorous. It's not appreciably, like your proof is very close to being true. It's just not quite right. It's very close though.
So should we not use that method for the test?
I mean, if I was to ask it, I would be happier if you used the Car-Theodori argument.
Okay.
Yeah. Which I did allude to in the statement of the homework. I gave you guys a link, I think, to my Calc 1 notes where I just said you go find it. Oh, so I made you work. That was my mistake. Let's see here. Anyway, let me stop talking about this. You asked me what's, how many questions on a test? Well, let's look at an old test. How about that? Would that be better?
Yeah.
There we go. Here's an old test. So this is from 2015. Question number 1. You got f equal to u plus iv, u equals blah, v equals blah. Where's the holomorphic? So nowhere. All right, great. You calculate them nowhere. Question number 2. I've got f of z is 1 over 3 plus z. Find the u and v. All right. Consider previous problem. Explain why this is equal to that and that equals to that without an explicit calculation of derivatives. So the point is, okay, well, it is this, so we know that the derivative is that, and we know f prime of z exists from that calculation, which means that the Cauchy-Riemann equations had to hold. Yeah. Let's see here. W equals 1 minus I. Calculate the Cartesian form of W to the 41st power. So you change the polars, you calculate the 41st power, you're done. Calculate the log of the sine of I times the natural log of 2. Leave it in Cartesian. So I take 1 over 2i of II log 2 minus II log 2, which is minus log 2, e to the log 2, that's 2. That's a half, and that's equal to, that, 3i over 4. What did I say to do? Oh, calculate the log of all that. Oh, yeah, so then I still got to log that thing. So I had to put it back into polar form in order to take the log. So the log of this is log of 3/4 plus pi I over 2. There you go. So I like to ask explicit computational questions about sines and logs and the stuff we've been tinkering with. Let's see here. Find a sharp bound. Oh man, I didn't make it to the end of the quiz. I need to go back to that. Wait a minute. Did my quiz?
You stopped at problem 12.
Oh yeah, let's talk about the rest of the quiz before I get back to the test. Sorry guys. I thought I was done with the quiz, but I just like, wait a minute. Oh yeah. So here we go. Order 0. I was just going to say, like, there's some stuff about showing the function's not one-to-one. Those are interesting questions. So you should look at my solution, I suppose, so that you could answer such a thing if I was to put it on. After all, it was on the quiz, so it's possible. But just to let you know what I did, basically, to show that it's not one-to-one in any neighborhood, I need to basically take an epsilon ball around the point and show that there's points in that epsilon ball which both give the same output for the same input, for different input. That shows it's not one-to-one. Like, it's not one-to-one if I can find two different inputs which give me the same output. And there are infinitely many ways to exhibit that. But for like this one, I used like -1 plus or minus epsilon over 2. When I do that, they both give you epsilon squared over 4. So they're different inputs, same output, not one-to-one on any epsilon ball of -1. So there's that. For part B,